Who would have believed that one day we'd be able to see this image? A black hole in the universe, a strange star from which no light or person can escape. This image was calculated using the equations of general relativity, a scientific theory of space and time developed 100 years ago. A theory that was in turn praised, rejected, forgotten, and then rediscovered. A theory that this black hole nearly killed. My theory.
The theory of relativity is infamous for its difficulty. I want to show that there's nothing peculiarly difficult about it.
Let me illustrate this with an example here. Let's imagine that this piece of jelly is the space. Then the presence of matter is to distort the space.
Einstein's theory of relativity does lead us into very strange and unfamiliar paths.
Relativity is perfectly intelligible to anybody who is willing to think.
In the 20th century, I was known by the name of Albert Einstein, and for my equation E equals mc squared. I sought to understand nature through mathematics. I had a new vision of the architecture of the universe, and I expressed it in a theory, general relativity. General relativity is a theory about gravity, the mysterious force that attracts stars and planets to each other. For 250 years before my theory, gravity was the realm of the great scientist Isaac Newton. My theory revolutionized the worlds of physics and mathematics.
Newton's theory of gravity, revolutionary in its scope and concision, had held water since the end of the 17th century. It is fascinating to think that to explain just a few changes to this law, everything had to be turned on its head. And that is exactly what Einstein did. His theory of gravity involves several major modifications. Space is no longer straight, but curved, depending on the matter inside. Giving a position at a given time no longer makes sense. Positions and times are intertwined, and geometry now has to be seen in 4 dimensions. And we can't count on this equation here anymore. It needs to be replaced by one with a radically different form.
First of all, I discovered that space and time were actually connected, working as one. And matter, such as stars and planets, bends and curves this space-time. That curvature is the gravitational field, obliging the planets to rotate around the sun. Nothing, not even rays of light, can escape the curvature. All these discoveries were based on a single observation, that of free fall, known since Galileo, and which can even be observed on the moon.
Well, in my left hand I have a feather, in my right hand a hammer, and I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. Mr. Galileo was correct.
I saw and understood free fall differently from all other people. It guided me towards the curvature of space-time. All I had to do was observe closely.
Einstein himself tells us about the moment when he understood that this was the tool that would allow him to form his theory. In 1907, he wrote, "I was sitting at my desk in the patent office in Bern when suddenly I thought that if somebody was in free fall, they wouldn't feel their own weight, and I was surprised." He realized that gravity has the property, and is the only force with this property, of disappearing as a result of its own effect. And that if we are in free fall, and so under the effect of gravity, we feel like there's no gravity.
In my day, I was only able to experiment this idea through thought. But 100 years later, the physicists of the 21st century have new tools, such as this tower in Germany, which can create a vacuum that eliminates air resistance. By dropping objects in capsules into the tower, we can see how, in free fall, our weight disappears.
In this experiment, we put two objects on a scale in this capsule, which will be dropped into free fall in the tower. The needles on both scales will fall back to zero, showing, albeit not particularly precisely, how this apple and this 1 kilo weight fall in exactly the same way in the gravitational field. So it looks like mass doesn't exist anymore, which may seem absurd because if we're able to eliminate gravity, then does gravity exist? Once sealed, the capsule will be raised to a height of 110 meters for a 5-second freefall in a vacuum.
So we have perfect conditions for every experiment that is done in weightlessness. Okay. So, for example, if we have some experiments for space, we can test the payload or the equipment in our facility.
Oh, thank you.
You're welcome. Here we have a view of the inside of the drop tube.
Okay, so 3.
Then after 1 second,
it will go 3, 2, 1. So now I'm a launcher.
So now we have to search for the right time in the video for the 5 seconds.
The 5 seconds. Okay. So this is after again.
Okay.
Something is happening. Okay. So now here we are during the free fall. It's almost zero on both sides. Gravity has disappeared. It worked.
Yeah.
Until now, this principle, the cornerstone of my theory, has proved watertight. Nobody has been able to prove it wrong. A team of French researchers is preparing to test the principle in space. Their satellite microscope, set for launch in 2016, will orbit 700 kilometers above the Earth and provide an unprecedented precision of measurement. But let's wait and see. In science, the experiment is our sole judge. Back in 1907, this idea, today known as the principle of equivalence, led me like a lighthouse in the night to rethink gravity. I returned to Switzerland in 1912 after 5 years of work. I returned to the city of my student days. The 2 years I spent in Zurich would be the most important of my life. I was offered a professorship in physics at the Zurich Polytechnicum School, now known as ETH Zurich.
So here's ETH.
One of my old university friends, Marcel Grossman, had become a professor there. He was far better than me in geometry. His notebooks inspired me on numerous occasions.
Impressive, no?
Yes, it's very detailed. The fundamental properties of elliptic functions.
He was preparing to work for Einstein, without knowing it, obviously. But that's what was going on. It's really surprising. I didn't think it happened like that.
What I would have done without Grossman, I really cannot say, because the mathematical obstacles before me seemed insurmountable. General relativity made me work like a monomaniac. To see if I was on the right track, I used a flaw in Newton's theory. Newton's gravitational equation couldn't predict the precise orbit of Mercury around the Sun. Mercury's perihelion, its closest point to the Sun during the year, shifted much too fast. This was a perplexing problem that physicists and astronomers just couldn't crack.
He arrived at the definitive theories in November 1915. Definitive in particular because he determined Mercury's perihelion with incredible precision.
After all these years, I still remember those evenings spent with Marcel Grossman in this café on the River Limmat, putting the world into equation. Our discussions concerned not only our studies, but ranged far beyond, over all the topics that could interest young people who kept their eyes wide open. It was here that my theory took form.
The key to describing gravity is the geometry of space-time. So, for the objects present in the universe, you have to determine the gravitational field they create, namely the geometry of space-time.
To do so hinged on solving an equation that took me 8 years to create. I wrote it as follows. G mu nu is equal to 8 pi g over c4 times t mu nu. A single equation and just a few mathematical symbols to describe our universe.
Based on a mathematical hypothesis, he opened up a new path, one that is still relevant today. It's incredible. You could have thought that it wasn't going to work.
But it did work. And it was here that the theory started to take on a life of its own, to unveil properties of nature that nobody had foreseen. Curved geometry implied that time didn't pass in the same way in all parts of the universe. Gravity influences time. The stronger the gravity field, the more time slows down. This threw everybody, myself included. In my day, it was impossible to test this prediction through experiments. Gravity on Earth is too weak, and its effects on time are imperceptible. But technology having evolved, in your day, this difference in time can be measured with amazing precision. The new atomic clocks in the basement of the Observatoire de Paris are the most precise clocks in the world, 1 billion times more precise than a quartz clock. Even at this level of precision, my theory still works. The effect is true everywhere. The universe does not tick to a huge universal clock as Newton thought. Each region of the universe has its own time. Each galaxy and each solar system exists in its own space-time. Looking at the universe involves looking at other times. In 1915, with World War raging, the publication of the theory of general relativity went unnoticed, gravity being elsewhere. But I did receive a letter from the German physicist Karl Schwarzschild. With my equations, he had succeeded in calculating the distortion of space-time generated by a star. This was a titanic achievement, given that my equation breaks down into 10 others, and each one of them had to be solved. But his work exposed a sort of minor flaw in the equations that nobody noticed. This flaw would later be called the Schwarzschild singularity. With his solution, Karl Schwarzschild cleared the way for the mathematical exploration of the theory. Unfortunately, this was to be the only letter I received from him. He died in the war in May 1916. The seemingly never-ending war prevented the circulation of scientific publications. But a ray of hope came to me from Great Britain, where I was nevertheless considered an enemy.
In Britain, in 1915, there was a British astrophysicist called Eddington, who was a pacifist, who was not at war. In fact, was still at his post in Cambridge. Now, it so happens that Eddington was one of the few people in Britain who was capable of understanding what Einstein was writing. and he immediately grasped the significance of this general relativistic theory.
The best physical test to confirm my theory was to measure if the rays of light reaching us from far away actually follow the space-time curvature. The Sun is the only close and available mass that can curve space-time in a significant manner. But if the Sun is in the sky, it is daytime, and the distant stars are invisible. Our only chance would be to photograph the starry sky during an eclipse.
The war ended in 1918, and the following year he led an expedition which went in two parts, part to the island of Principe, off the coast of Africa, and to Brazil. Weather wasn't totally favourable, the observations weren't brilliant, but they were sufficient to show that light was bent in exactly the way Einstein had proposed. And when he came back, Eddington did a number of presentations and huge popular lectures about this work. And I think in the English-speaking world, that launched Einstein.
Eddington presented his results to the Royal Astronomical Society, standing before a large portrait of Newton that had sat there undisturbed for over 2 centuries. Reportedly, the whole atmosphere of tense interest was exactly that of a Greek drama.
Napoleon and other great men of his type, they were makers of empire. But there is an order of men who get beyond that. They are not makers of empire, but they are makers of universes. When they have made those universes, their hands are unstained by the blood of any human being on earth. Ptolemy made a universe which lasted 1,400 years. Newton also made a universe which has lasted 300 years. Einstein has made a universe, and I can't tell you how long that will last.
After my theory was confirmed, I received invitations from around the world. During one of my trips in 1921, I found out that I'd been honored with the Nobel Prize for Physics. Strangely, I didn't receive the prize for general relativity, no doubt still too controversial, but for my previous work. There was little talk of my theory of relativity. As Charlie Chaplin once said to me, they're cheering us both. You because nobody understands you, and me because everybody understands me. When I was in Paris in 1922, people wanted me to talk about time. I recall people talking about it more in philosophical salons than in scientific conferences. The fact is, nobody there understood the slightest thing about my theory. But my most vivid memory is of a conference at the Collège de France. A French mathematician, Jacques Adhémar, stood up and pointed at me threateningly, pointing out a supposed flaw in my theory. He brought up the very mathematical flaw that had escaped me in Schwarzschild's solution.
That's the Schwarzschild solution from 1916.
If I understand correctly, r is the radius relative to a central point, namely a star?
Yes, it's a star, and its mass is m.
Okay, but you can see straight away that there's a problem. Because if I see a radius equal to 2gm divided by c squared, the coefficient here becomes 0, which isn't right. And here you get 1 divided by 0 equals infinity, which is even worse. Your solution falls flat on its face.
That's exactly what Jacques Hadamard said to Einstein in Paris. It was terrible for Einstein because here, obviously, we're talking about maths. But think about physics, which, for example, determines the geometry around our sun, the sun in the solar system. Imagine we send a satellite towards the sun. What happens when the satellite gets to this point? Does it stop? Does it explode? Or does it disintegrate?
And that must have been seen as a fatal blow to Einstein's theory, right?
It did pose a major problem for Einstein because his theory was supposed to determine the structure of space-time, and for a particular solution, he saw that there were places where the idea of space and the idea of time no longer made sense.
The end of the world in equation form.
That's right, the edge of the world, what we call the Schwarzschild singularity.
No doubt this all looks abstract to you, a few symbols on a blackboard. But for me, this singularity was a real monster. It resembled a sphere, an impenetrable black bubble, a place in the universe where time seemed to stop and where space no longer existed. The sphere appeared at the center of all celestial objects, like a star. Fortunately, after a few calculations, we discovered that for our Sun, the size of the singularity was just 3 kilometers, hidden inside. For it to become visible in our solar system, we would need to be able to condense the entire mass of the Sun into a 3-kilometer sphere. For astrophysicists, then, the singularity remained imaginary. But mathematicians had a serious problem on their hands. Would it prove fatal for my relativity? Soon, the entire community was talking about the singularity. And apart from a few firmly convinced cosmologists, pretty much everyone dropped my theory.
These were hard times for Einstein. After his glory days, when relativity was in all the newspapers, when he was the star of the Parisian salons and spent the 1920s traveling around the world, he was the most heralded scientist of the day. But interest in his theory shrank dramatically, and life for people working on relativity became difficult.
With Elsa, I moved to Kaput near Berlin. I took up sailing as a hobby, until the day when events forced me to leave my homeland in 1933 forever.
Dr. Einstein, who gave the world its biggest headache, is back in California again with his wife. They've been fog-bound all night in San Pedro Harbor. The professor had a theory as to how they could land, but before he and the captain could figure it out, the fog had all gone away. Now he's going to the Institute of Technology in Pasadena to work with other distinguished scientists. There his theory will be thoroughly discussed and analyzed, and if it is what he says it is, why then everything will be all right, won't it?
Physicists were extremely wary and not very interested. There was a certain amount of aggression from physicists in particular, except for the people who believed in it, who were few and far between. And then there were those who simply didn't want to try and get their heads around it.
The problem of singularity grew as the years went by. The impenetrable sphere, hidden in the heart of the stars, remained an obsession, impossible to understand, to imagine. The edge of the world. Relativistic scientists working on the gravity of stars such as our Sun found that, according to my theory, stars could die. That really was the limit, because the theory appeared to say that in dying, the star imploded and its size reduced to approach that of its singularity.
So stars are born and live and die. The Sun's future history is fairly simple, not good for us on Earth. The Sun will go through several phases, including swelling. Then it will ultimately shrink to one of these white dwarfs and will steadily cool thereafter, just stop producing energy, stop its fusion reactions, but still quite hot and cooling. For a star that's much bigger than the Sun, basically what happens is the core of the star collapses to make a neutron star. The rest of the material suddenly finds it's standing on nothing, goes rushing down to get a foothold, meets this very, very solid neutron star and bounces out. And 90 or 95% of the material of the star goes out, and the other little bit remains.
This extremely dense neutron star, with a radius of barely 10 kilometers, is coming dangerously close to the Schwarzschild singularity sphere hidden in its center. The risk I immediately saw was that it could be discovered in the theory that stars could condense even further and their singularity escape from within.
The question that immediately comes to mind is, do we know any stars whose Schwarzschild surface, the edge of the theory, is on the exterior of the celestial body?
You would have made an excellent physicist, or even astrophysicist. Can we find any solutions in which we have the star, or the celestial body, and here, the Schwarzschild singularity?
Those are probably created from really massive stars. Once that big star begins to run out of nuclear fuel, gravity wins, so the star shrinks. That puts up the gravity at the surface of the star, so it shrinks, which puts up the gravity at the surface of the star, so it shrinks. And it shrinks right down. And even the atoms, you know, things like this table and chair are made of, the atoms collapse and the nuclei collapse. And if you believe the theory, it collapses down to a point, which is zero radius. Some people don't like these kinds of points and zeros, so that's debated. But it goes down to very, very, very small, having been one of the biggest stars in the universe before. And it's a black hole.
All of a sudden, mathematicians and physicists were telling me, Einstein, that the Schwarzschild singularity, the flaw in my theory, could in reality exist in the real universe, stepping out of the world of mathematics like a magical sphere. And a completely black sphere, a place where space and time disappear. I didn't want to believe it. For me, the singularity had to remain a mathematical hypothesis.
A star can't just cave in like that. Cave in, not stretch, but implode. It's not possible. There's something unbearable about that.
Other people, in particular Eddington, thought there must be something wrong. He thought there must be something wrong in the calculation, but if not, there had to be something wrong in the physics. So he thought, you know, nature shouldn't behave like this. But then it is a strange way for nature to behave, which is very different from the sorts of things that one is used to.
The most extraordinary thing in all this was Einstein himself. He didn't want to believe that the Schwarzschild singularity could really be manifested, so he set out to prove it. The worst paper he ever wrote. He took the conclusion he wanted to reach as the basis for these calculations.
The main result of my research clearly concluded that Schwarzschild singularities didn't exist in physical reality.
It really was a poor paper by Einstein, one of the worst, but we can forgive him because he did write some excellent ones too.
It was all too much for me. My own theory had completely escaped my grasp. Since the mathematicians had invaded the theory of relativity, I did not understand it myself anymore. In the USA in the 50s, I was seen as a sort of fossil, made deaf and blind by the years. Ultimately, I didn't mind that role. It suited my temperament. Shrouded in this mystery, I left our planet. And I can guarantee you that the most beautiful thing we can experience is the mysterious. The doubt persisted after my death. The black hole continued to disturb. A number of competing theories showed that it can't even exist because, logically speaking, a star cannot simply collapse to zero. But the life of relativity would be changed by the 1960s and the British.
Well, according to Einstein's theory, a black hole that results from the collapse of a star several times the mass of the Sun would be an object several miles in diameter. But if you, say, imagine the Earth compressed right down until it became a black hole, the dimension would be a bit less than an inch, something like that.
That's the Earth?
The Earth would have to be compressed into that size to be a black hole.
Roger Penrose had, like myself in my day, ideas that came to him entirely unannounced.
At the time I was getting very interested in this, which was about 1964, perhaps a little earlier than that, and there was a lot of interest in gravitational collapse at that time. Well, I was pondering over these issues at one time. I was, at this time, at Birkbeck College, where I was a lecturer, and a colleague of mine, Ivor Robinson, who was also had an important influence in many aspects of general relativity. And he was talking to me very excitedly about certain things. I forget what they were, I'm afraid. But we came to a road, and when we crossed the road, the conversation stopped. And when we get to the other side, instead of walking into a wall,
yeah.
I forget what I had, the idea I had, which was crossing the street here, you see. And then he goes off later.
Yes.
And then I try to remember why I feel happy.
Yeah.
Why do I feel happy?
Yeah.
I have no idea. So I think, my breakfast? No. Ordinary breakfast. So on, you see, all through the day. And then think, aha! I had this idea about how you could characterize a collapse of a star to a point where it is gone too far, point of no return.
Yes.
And this was a surface, which I call a trap surface. And this surface can be irregular, can be not symmetrical, but it has a very curious property that the light on both sides is focused inwards. And I knew I could use this condition to try to prove a theorem.
Roger Penrose put into an equation the black hole that had thwarted so many physicists before him, myself included. He proved definitively that when a star collapses, all its constituent matter condenses into a single central point, an infinite density of matter, a point where time stops. Roger Penrose worked with some important people, and most decisively with the young physicist Stephen Hawking. The two earned a medal from the Royal Astronomical Society for their work on black holes.
Well, I haven't seen this before. Yes, proposal for the Eddington Medal, that's what it was, yes. I talked to Stephen at that time, and we had quite a long discussion on the details of this type of argument, and this had a big effect on what he did later. He generalized the argument to cosmological situations, and then later on, we got together and had a general theorem which seemed to encompass pretty well all the things that had occurred earlier.
I'd been dead for 10 years, I think, and this time I had to accept that my theory predicted the existence of black holes. Despite everything, even if the work of Roger Penrose was convincing, nothing proved that these singular celestial bodies arising from the death of stars actually existed. It was all purely theoretical. But new means of astronomical observation were developed in the 60s, and a young British scientist was to change our vision of the universe forever. Her name is Jocelyn Bell Burnell.
Radio astronomy revealed new kinds of objects, things that did not look particularly conspicuous or spectacular to the optical astronomer. My first 2 years were spent working in the field, constructing a radio telescope. By the end of my PhD, I could swing a sledgehammer, which was not a skill I expected to acquire, but I did. We started observations in the summer of 1967. And after about a few weeks of observing, there was the first indication of a curious signal. And then I turned my attention to this thing, which meant going out to the observatory each day just before the telescope turned to it, switching to a high-speed recording, and it turned out to be this string of pulses, about 1 1/3 seconds apart, which was not something I expected, I have to say. We hadn't known about anything like that. We hadn't imagined that anything like that could exist.
But the universe doesn't change in a day. Jocelyn Bell Burnell came under heavy criticism until she detected, after months of unflagging work, a second similar source.
Ha! What's that? That looks a bit like the first signal that we've been chasing. That bit of sky will be seen by the telescope at 2 o'clock in the morning. It was very cold and the equipment wasn't working properly in cold weather. It was some problem with the receivers. And of course, when I got there, it wasn't working properly. But I got it to work properly for 5 minutes, and it was the right 5 minutes as the telescope was looking in that direction, and it was the right beam setting, and in came pulse, 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 pulse. And that, for me, was actually the eureka moment, the sweet moment, because you know it's not the equipment with the fault, you know it's not interference. It really does begin to look like a new class of object, still don't know what.
Well, these signals that we're picking up are entirely new. Nothing like this has been seen in radio astronomy before.
Here is a discovery which illustrates the universe is far more complex than we at present believe.
It's not showing any sign of tiring, which means it's got lots of energy, which means it's big, but because it's going fast, it's small. So it's big and it's small. That didn't make sense for a while, until we got our questions a little sharper. It's small in the sense of how wide it is, but it's big in the sense that it's got a lot of mass. Not that it's physically big, but that it's got a lot of mass. And we can see with hindsight that these very, very dense stars, which are small and massive, actually explained it.
Jocelyn Bell Burnell had discovered a pulsar. And everything seemed to suggest that a pulsar was a neutron star. The remnants of the death of an extremely dense star, neutron stars are the closest thing to a black hole. So my theory was right, and in the end, I was wrong to doubt it. Anyone who has never made a mistake has never tried anything new.
It became clear then that all the theoretical hypotheses posited earlier on, what was possible on how stars evolved, how they died and how they can collapse to become neutron stars, were true and correspond to phenomena in the real universe, which also meant that the next step, i.e. that if you have a dead star but one that is too massive to be a neutron star, and so according to Einstein's theory, has to be a black hole, was that black holes exist too. And after the discovery of pulsars, the conceptual landscape changed, and everyone considered it clear that not only did neutron stars have to exist, but that black holes had to exist too, and that we would find them one day.
The gravity on a pulsar is very, very strong. You've got the mass of the sun, 1,000 million tons, all in a ball 10 kilometers across. And this produces some curious effects. Curious to our minds. They're explainable by general relativity. One is that the gravity bends light rays. So if I look that way on the surface of the pulsar, I actually see over the horizon. I see over the horizon in every direction. And it also affects clocks. If I'm on a pulsar and you can see my watch, you see the second hand is making 1 tick every 2 seconds because the gravity has slowed the clock so much. I can use my watch, take my own pulse, and it's okay. But that's because the gravity has slowed my heart the same way, and my metabolism. And actually, I have problems getting onto the neutron star, the pulsar, because as I come down to land, I am pulled down by this very strong gravity. But there's a very strong gradient of gravity. The force on my feet is much stronger than the force on my head. your body gets stretched. There's a technical term for this. It's called spaghettification, after spaghetti. But actually the difference in force between the bottom of your body and the top of your body is so strong, it breaks. Your body gets pulled apart. Your feet get pulled off your legs get pulled off your body, your head separates from your body, and the different bits of your body drop onto the neutron star, one after the other. So don't go there. Not a healthy space.
The universe is far stranger than I dared to imagine. The famous Schwarzschild singularity, an impenetrable sphere, actually represented the edge of a black hole. But what actually happens if we try to cross it?
This surface has an extraordinary property. It isn't material, and yet it separates space-time into two zones, each with different properties. You can cross it in one direction and send light from the exterior to the interior, but you can't send light from the interior to the exterior.
It's a trap you never get out of.
A black hole is above all a solution to the theory of general relativity. It is a mathematical solution, a space-time configuration, a universe. And the question is finding out if this solution actually corresponds to something in the physical world.
We aren't sure that black holes exist in the real universe. There are strong signs, though they remain indirect. But the entire evolution of astrophysics in the 20th century, the fact that stars are born and die, that very dense dead stars exist, such as neutron stars, and that neutron stars have a maximum mass, all this strongly indicates that black holes must exist in the real universe. Maybe we will find absolute proof in a few years.
Finally, my theory of general relativity has found its field of application. It describes the infinitely large. Astronomers today are following in the footsteps of Roger Penrose, Jocelyn Bell Burnell, Thibaut Damour and many others as they search for the existence of black holes hidden in the immensity of our universe. Without relativity, there would be no Big Bang theory, no relativistic astrophysics, and not even a scientific cosmology with which to speculate on the origin of our universe and its future. That said, as always in science, each new discovery brings with it new questions, and the black hole concealed yet another surprise over its horizon.
So if you go inside a black hole, you should find a point at its center, because if a star collapses in on itself, it crosses the horizon. But what does it do after that? It collapses. And what happens? General relativity says that the fabric of space-time tears, and that a true space-time singularity now exists at the center of the black hole. In other words, space-time has ceased to exist.
It gets swallowed by the hole. And then that information is lost to the universe. Now, you see, this is not something people like. I can see there's some feeling of unhappiness from you on this position point. You're not unique in this, I may say. And it's probably the majority view amongst physicists now that the information somehow has to get back again. Maybe into another universe, maybe gets out through some curious effects of quantum mechanics, one way or the other. Personally, I think it has to be lost.
Today, I enjoy watching all these relativistic scientists from afar as they try to resolve new mysteries. From string theory and loop theory to non-commutative geometry and twistors, a number of ideas have emerged to try and go beyond my theory. One such speculative idea has been developed by Carlo Rovelli.
General relativity works very well, but it clearly tells us that it doesn't work in the center of the black hole, where singularity takes hold. And this is where we need quantum mechanics, and for which we have a theory of quantum gravity that should tell us what is going on. What that theory tells us or suggests is that afterwards it bounces out and boom.
Hold on. If you say that it bounces out, then you should be able to see loads of little explosions everywhere, so why don't you?
Exactly. That's the magic of the theory. Because if you were on the star and strong enough to resist all that pressure, then that rebound would be practically immediate, a few milliseconds. Except that in general relativity, time passes at different speeds in different places. In a black hole, that effect becomes enormous, very, very strong. According to our calculations, a millisecond inside a black hole corresponds to billions of years outside.
Okay.
So if this image is correct, what is a black hole? It's a star that becomes extremely small, a Planck star, and then bounces out and explodes. But seen from the outside, the whole thing happens in slow motion, extreme slow motion, taking billions and billions of years. I think that a mystery lies at the heart of physics, a mystery that is yet to be solved. And that mystery is the nature of time. What really is the passing of time? We've discovered that time is not universal as understood by Newton. We've discovered that each person has their own time. We've discovered lots of things about time. But what really is the passing of time? We don't know. The theory my colleagues and I are working on, loop quantum gravity, has a set of equations limited to general relativity in one case and quantum mechanics in another. These equations are special because they have no time parameter in them. So time is not a fundamental ingredient of the universe. Obviously, as with all theories on quantum gravity, we are not sure because we have not yet to establish measurements providing the theory. But I think that on the whole, everyone is convinced that putting general relativity and quantum mechanics together changes something fundamental in our understanding of space and time.
To tell you the truth, I would never have wagered that 100 years later, my theory would still be around. I thought by this stage you would have replaced it with a better one. Now you have to unite quantum theory with my theory of general relativity. I'm convinced that this will once again revolutionize our vision of space and time, as my theory revolutionized the vision of Newton.
Isaac Newton, with Einstein, was able more than anyone else to see further, to see more things and discover more things in the world. In a letter he wrote at the end of his life, there's a beautiful sentence in which he says that he doesn't know exactly how others will see him or how they will remember him, but he sees himself as a child on a beach, playing with pebbles, a child who is happy because he has found some particularly beautiful pebbles, while in front of him lies the immense ocean of all the things he has yet to understand. And I'm sure that Einstein shared that same sense of the immensity of all we have yet to know.